Greetings. Good morning or good afternoon, depending on where you are. We are continuing with our thermodynamic lectures. Today we want to look at open systems, steady flow in open systems. And the one we are going to focus on today is the simple water tube boilers. And we might look at surface condensers. And one of the first things we always remember the steady state flow equation for energy flow equation, that is dH, we say plus dC squared over 2 plus G dZ is equals to dQ minus dW. This was the steady state flow, energy flow equation. Very important for us to remember that. And in this particular case, remember that represented the kinetic energy expression, and this represented the potential energy expression. And of course, Q and W have their usual meaning, that is Q is heat and W is work, and of course H, dH represents the enthalpy. Now, so let us look at, let's consider a simple water tube boiler. Example where we have an open system and we have a steady flow. So if we draw the schematic, if we draw some schematic representation of this simple water tube boiler, let's draw it here. So we have our system. This is just a sketchy illustration to help you understand. It's not perfect. So we have our tubes. This is not a perfect drawing. That's for illustration purposes. For illustration purposes. So we have vapor out. Let's call that outlet 2. Then you have, of course, fluid in. Let's call that state point 1. I call that state point 2. So we have fluid in. So this is just an illustration. So we have the fluid coming in and vapor leaving out. So we have the furnace gases. This is to flue. This is furnace. This is in, because there's the heat. So we have this fluid coming into the system, and of course it will exist as vapor. So the fluid comes in, the liquid comes in, and leaves as vapor, and this is at a constant rate. So the fluid, the system, and leaves as vapor at a constant rate. That's very important for us to note. Of course, in this expression for steady state flow equation, the elevation is of no significance, so we can assume that is 0. So elevation is not significant, it's not significant, therefore GdZ can be assumed to be 0. And again, the velocity of the fluid flowing through this particular system, the velocity is low. Therefore, the kinetic energy at the entrance and at the exit the difference is insignificant. So we can assume that the kinetic energy change is insignificant or 0. Again, the fluid velocity is low. Therefore, the kinetic energy at entrance and exits 1 and 2 therefore the difference in kinetic energy at entrance 1 and 2 is insignificant. Thus, well, we can say dc2 over 2 is basically 0. So the difference between the kinetic energy at the entrance 1 and at the exit 2, we can assume that it is insignificant. The difference is very negligible, so we can assume it's 0. So that we are left with our body of equation. So we are left with our main equation. Let's go back to our main equation there. Now that the elevation is not significant, and the kinetic energy is not significant, then the steady state flow equation is left as, therefore the steady flow equation is left as dH is equals to dq minus dw. But it's also important to take cognizance of the fact that when this fluid flows through this particular system, the fluid is not doing work. It's not doing work, neither is work being done on the fluid. And therefore the work in that particular system is 0. Note that as the fluid or liquid flows in the system, it is not doing work, nor work done on it. Therefore, what does that mean? W is equals to 0. So the equation, the steady flow equation, reduces even further. So therefore, the equation still now is dH is equals to dq. And of course, if you take it between the two limits, that's the entrance and the exit, take it between the two limits, that's the entrance and the exit, that is integrating the entrance and exit as our limits, then we have the integral of dH 1 to 2 is equals to integral of dq 1, 2. Always remember, Q and W, that is work and heat, are path functions. So when you integrate those quantities, you don't get the change, Q2 minus Q1. But because H is a state function, which depends on the state of the system, when you integrate, you get the difference between those two quantities. So therefore, we have H2 minus H1 is equals to Q. Note, always remember, Q is a state function. Q is a path function. And therefore, it is not an exact differential. Therefore, it's not an exact differential. So that if you take the integral of dq, you simply get q. Note, you don't get q2 minus q1. It's nothing like that. Don't get q2 minus q1, because that's a path function, so it's not an exact differential. So get these particular quantities. So what is q? Q therefore is basically the heat which is used in the production of unit mass of vapor. The heat in the production of unit mass of vapor. So if, for example, you said that the mass of that vapor was m kilograms per second, then Q will be the heat per second. If the mass vapor is m kilogram per second, then Q per second. So for that corresponding mass. So this is just a simple water boiler. Let us now look at some surface condenser. A simple surface condenser. For the simple surface condenser. And notice one thing, before we move to a simple surface condenser, that to calculate the amount of heat, you only need these thermodynamic quantities at the entrance and at the exit. And then you're home and dry. Now, let's look at simple surface condenser. So we have a simple surface condenser. So again, this is not drawn to scale. It's just a sketch for illustrative purposes. Sketch for illustrative purposes. So let us say we have these tubes. So we have these tubes, trying to do it as best as I can. So we have these tubes. Let us just say that we have a coolant. In. Coolant is very important. For example, if you look at reactors like continuous stirred tank reactors, we have coolants. For example, if you have in that reactor an exothermic reaction where a lot of heat is produced, one way of managing that heat is to have a coolant circulating as a jacket around that reactor. So in the case of continuous stirred tank reactors, you see coolants which is circulating around that reactor so that you are able to dissipate that heat in that particular system. It acts like a sink for that particular heat. So we have coolant in, coolant out. And then we have vapor in. Let's call that again, that state point, that entry 1. And of course, we have the condensate out. Notice now at point 2. In the other one, we have the liquid in, vapor out. Now we have vapor in and coming out as a condensate. And why does the vapor come out as a condensate? When it goes through these tubes, when it goes through this array of tubes, this array of tubes are cooled by this coolant. So the temperatures are relatively low, so the vapor will condense. So let's just note that the vapor goes through the array of tubes which are at a lower temperature due to the circulating coolant, which acts as a sink for the heat. So you have our heat there. And so in this particular case, you'll have your vapor, it is cooled, comes out as a condensate. So the vapor is cooled, comes out as a condensate. Vapor cooled and exits as a condensate. In other words, it is condensed as a condensate. Now, the only difference between this and the simple water tube boiler is simply that the expression will be the same. For the steady state flow equation, the expression will be the same, only that in this particular case, so expression still remains for steady flow. Expression is still H2 minus H1 is equals to Q. The only difference in this particular case is that H1 will be greater than H2. Only that H1 is greater than H2, therefore Q is negative. We'll be having a negative value. So steady state flow equation is very handy in dealing with practical engineering problems, and technological problems. And so you can simply calculate value, for example, the quantity of heat just from the thermodynamic quantities at the inlet and at the outlet without necessarily being too concerned about the actual properties of the fluid which is flowing within that system. And of course, that normally is the basis of fluid dynamics, which we are going to work with as we move through with our lectures here. So let's stop at this particular point for today.